17.4 discusses free energy. So first we're going to talk about this new formula we have. We have G equals H minus T times S. So here our S is going to stand for entropy. Our T is going to be temperature, and that's going to be in Kelvin. Our H is enthalpy, and our G is going to be Gibbs energy. These are all state functions. So next we can talk about our Gibbs free energy. So when delta G is less than 0, the reaction in the forward direction is going to be spontaneous. So that's when our delta G is a negative value. Now if our delta G is equal to 0, then our reaction is at equilibrium. And there'll be no net reaction. Then if our delta G is greater than 0, the forward reaction is not spontaneous, but its reverse reaction will be spontaneous. So the equilibrium position in a spontaneous process is given by minimum free energy and is available to the system. The free energy decreases until it reaches this minimum value. So we do have standards when talking about our free energy formula up here. So our standards are pure solids and pure liquids. We also have 1 atmosphere. We also have 1 molar for concentrations. Then we have our delta G is going to equal 0 for elements. And then for temperature, our standards are 25 degrees Celsius or 298 Kelvin. So you can also find free energies of systems and whatnot by using this delta G naught is equal to the sum of all of the products of free energy, or free energies of the products, minus the sum of all of the free energies of the reactants. So for our first example, we're given that delta H, which you recall up here is our enthalpy, is equal to negative 93.8 kilojoules per mole. And that's going to be important. Pay attention to our units. Then we're given delta S is equal to negative 156.1 joules per mole times K. So in this particular situation, our delta G is going to be equal to 0. So then the way we're going to set it up is going to be delta T, because the T's on we're not given, so we're looking for temperature, is equal to delta H divided by delta S. So if we plug that in, we have negative 93.8 kilojoules per mole. And then I like to go ahead and just convert straight over to kilojoules, because that's what we're going to be working in with both of these. So I always convert my delta S to kilojoules before I continue. So if we move that just 3 spots, we're going to be dividing it by negative 0.1561 kilojoules per mole times K. So then we get rid of kilojoules per mole, and we're left with K. So then once we have used our calculator to figure that out, we have our delta T equaling 601 Kelvin. So in the next example we're given delta H is equal to negative 99.84 kilojoules per mole. Delta S is equal to negative 16.80 joules per mole times K. Our T is equal to 298. So all we have left to find is our delta G. So when we go from here, we're going to set it up negative 99.84 kilojoules per mole minus, we're at 298 Kelvin, times, and remember we're going to go ahead and move this, we need a 0 here, so negative 0.01680 kilojoules per mole times K. So once we've done these calculations, we find that our delta G is equal to negative 94.83. So up here, we already had our delta G, and it was equal to 0. That means that it was at equilibrium and there was no net reaction. But down here, we have a negative. And if you recall from earlier, our negative means that in the forward direction, our reaction is spontaneous. So its reverse reaction would actually be not spontaneous. So that is it for our free energy.